To start off this afternoon's session is Dr. Giulio Ruffini, who's born in Barcelona. He got his bachelor's in mathematics and physics from Berkeley, his PhD from UC Davis, and after his PhD joined the Institut d'Estudi Especiali de Catalunya, where he developed algorithms for GPS, radar, and EEG analysis. He founded StarLab Barcelona as a director and researcher, and he defines himself as a physicist, but his interests spill over into other fields, including neuroscience. He's been involved and led several ESA and EU projects on technology development in Earth observation and neuroscience, mostly related to electromagnetics in the brain. And in 2010, he became president of Neuroelectrics, a StarLab spin-off focused on the design and development of brain monitoring and non-invasive stimulation technologies. So join me in welcoming Dr. Ruffini.
Thank you very much for the kind introduction and for the opportunity to come to Hawaii, which is one of my absolutely favorite places in the world. So thank you very much. So I'm going to give you a talk today trying to cover a little bit more of the physics angle, as you can probably guess, on brain stimulation. And so I have a part which I will probably go fairly quickly over. It's an introduction on tDCS. Let me start the clock here. We'll discuss mechanisms, mostly on the immediate effects of tCS, modeling aspects, and then touch on the limitations of classic montages and why we need more sophisticated tools, which come by the name here of tCS, multi-channel transcranial current stimulation, to provide more focal stimulation and also to target extended targets and networks. And then some notions on combining EEG and tCS, tACS and beyond, and some future outlook aspects. Okay. As a disclosure, you saw it from the introduction. I work for StarLab Neuroelectrics, which is mostly Neuroelectrics is really focusing on the development of these technologies for products and services. Okay. So tCS is the term that I've coined basically to include all kinds of brain stimulation that uses low intensity currents. Current control systems is the key word here. Non-invasive, which are delivered through 2 or more scalp electrodes. tACS, alternating current, and tRNS are similar to tDCS, but have time-varying currents. The term tCS is meant to include all of this. Okay, and sometimes we will use the term tCS to talk about the multi-channel systems. Here on the left, you have a picture of a classic traditional transcranial DC stimulation, and I will be talking about what the evolution of these systems is now. And I couldn't resist but put a ticket from the AC/DC concert that I just went to a couple of weeks ago, which has the nice terms AC and DC in there, and for the same reason, I think. Alternating and undercurrent is what inspired them. So very quickly, transcranial current stimulation involves the application of current control systems. Currents are injected in the brain, and weak electric fields and low frequencies are used, so we can use what we call in physics the quasi-static regime. The firing rates of neurons increase, as I will explain in more detail in a moment, when you apply it in the right way, or it can be decreased as well, and as a result, you have plastic effects. The power dissipated by tDCS devices in the head, or tCS in general, is very small. It's like 0.05 watt, and mostly is delivered on the scalp, which is what has the most resistance. And as a reference here, I included some reference to Federal Communications Commission recommendations for GSM, SAR. These are radio power delivered to the body, and as you can see, it's much greater than what we can do in tDCS. So from that point of view, you can already infer it's a very safe technique. The current is normally applied for about 20 to 40 minutes. It's been known for centuries in a way. Even the Egyptians were using electric fish to try to treat their pharaohs for migraines and things like that. The recommendation is do not try this at home with fish or else. A slide here comparing TMS and tCS. It's an old slide from 2007, I believe, from work from Tim Wagner and others. And they were already trying to understand, through modeling, the difference between TMS and tDCS. And you can observe already in these crude models that you have more focality with TMS than with DC, with the type of electrodes that were used at the time. This is a more modern rendition. This is actually a very recent work from Ricardo Salvador and Pedro Miranda. And it just shows a comparison of the typical electric field you generate with DC stimulation on the left, and on the right, what you can get from TMS. Two main points are, you are not stimulating where you think you're stimulating with DC stimulation. It's very widespread, as opposed to the TMS, which is much more focal. And also the intensities that you can see here in this plot, the scales, one of them goes to 0.4 and the other one to 178. So you can see that there's quite a big difference in that. However, as I will explain, if you use smaller electrodes and you use them in the right way, you can also get much more focality. And as you can see on the right-hand side there, it's a 5-electrode optimized montage for M1. And you can actually get much more controlled stimulation as compared to the previous slide anyways, although the intensities are still smaller. My note on the limitations of bipolar montages with sponges, which is what is being used still quite a lot, I think. First of all, these large sponges imply that you have large impact areas uncontrolled, in the sense that you are stimulating a very large portion of the cortex, and the results from that are going to be hard to interpret, at least. If you use square electrodes, there's even the complication of you should really specify carefully how you should orient these electrodes if you want to have some reproducibility of what you're doing. In addition, sponges are noisy. As was mentioned before, it's an old technology, and it actually, for the transmission of current, it wastes a lot of energy, and this makes noise. It makes pH changes, and it's really not an optimal way of doing things. But it's what people seem to like to use, mainly from tradition and from reading older papers, I suppose. Mechanisms. Okay. Just to point you to our wiki here, we have some of the things I will be saying are there are papers and even a book that we wrote in the Hive project, which is the origin of all this story for me in 2008, where we did a nice review of the state of the art from the biophysical point of view, really. I'm going to skip this. I just wanted to, because sometimes I feel I get questions sometimes, and I realize that maybe some notions are not very well explained. We have Ohm's law, which you're probably very familiar, that talks about the voltage that you need to inject a current through a resistive medium. This is generalized for conductive media to this equation here that basically relates the currents, the current densities, which is a vector quantity, and I put a nice vector display there on the right to put in the context, is proportional to the electric field. So these two quantities are proportional to each other. The other thing that's interesting is that if you have conductive media with different conductivities and you make currents flow through them, you will have charge accumulation at the boundaries. This charge accumulation is actually what gives rise to the secondary electric fields that you are inducing in the system. And we should keep this in mind. From thinking about slices and the experiments that I will briefly discuss in a moment, I thought I would give you here a picture of one standard setup, or one setup that has been used in vitro, in which you have parallel plates across which you put a voltage and you inject currents, And this can be, in this case, there are two sets of parallel plates opposed to each other. And if you control the voltages and the currents, you can control the orientation of the electric field. And here you have cortical slice with some imaginary neurons aligned in some direction. Okay, I just wanted to put that in there because I will refer to it in a moment. But also to briefly mention that the head is really acting as an electrolyte when you're injecting currents, and what's actually moving are electrons, but they are not moving freely. They are moving across ions, and that chemical reactions will take place to allow for the transport of this charge. And this is also an interesting thing to keep in mind to understand what tDCS is doing. Okay, so since I don't have that much time for all the slides that I have, unfortunately, I just will go over briefly some things. So just some examples of papers, old papers now, but important papers that showed things like the orientation of the electric field is important. The orientation in relation of the orientation of the neurons is important. You can try to think about this physically and model it simply. So here's a very simple neuron. So on the top you have a very simple neuron. On the bottom you have an even simpler neuron, which is just a sealed box with some ions inside. And you can use this model with a thin membrane here. You can use this model to start thinking about what's happening when you put these electric fields across it. So here's a very simple model. You have these plates here. You're putting in a current through them. You create an electric field. This neuron is sealed. Inside you have an isopotential because currents cannot flow. And the thing that you notice immediately is that the difference in potential between the neuron and this part here and this part here is greatest. And that's where you have this transmembrane potential change. This simple model already shows to you that if you put a neuron in a field, it will have these transmembrane potentials at the end, which is what we think about. And here's the electric field actually in the membrane. And as you can see, well, the length, I mean, if you start thinking about it, you will see that the length of this box will make an impact on how strong this field is. Here's a slightly more sophisticated neuron, but still trying to capture a bit of the geometry. But the end result is the same. So you see that you have these transmembrane potential alterations. Of course, if you want to really understand what's going on, you should try to model more realistically what is happening with more realistic neurons. But this is hard to do. I think it needs to be done. And also to understand how these neurons interact with each other is the next level of complication. But we have tools now to do this. This is another slide I normally show because from Maram's work in the past, showing that as these earlier simpler models were showing, it's kind of a linear relationship between the electric field strength and the transmembrane potential. Okay, so you have a linear effect, which is the other thing that we can keep in mind. And if you put all these things together, we end up with some of the notions that were put forth before by Peter's talk on I think it's called the cortical model, is what you call it in the TMS world, which just says something like the transmembrane potential, it's basically proportional to the electric field dot product with a general orientation parameter of the neuron. And here's a picture of that. So you have here this pyramidal neuron. This length scale lambda has to do with the length of the membrane and other things. So the longer the neuron, the better. And if it's aligned with the electric field, that's where you will pick up the most effect. Okay. Next. Is the concept of coherence, and by that I just mean if you have a bunch of neurons that are aligned in the same direction, then the effect will be bigger, okay? And this applies to tDCS, but it also applies to EEG in the same way. And one of the themes of my talk today is that EEG and tDCS share a lot of things from the physical point of view anyways. okay? The next level of modeling would be going into trying to model what happens in the entire brain, and this is work that we did with Isabelle Merlet and Fabrice Wendling some years ago now, trying to put together an end-to-end simulation of what's happening. So modeling the electric fields that are generated in the brain using a heuristic head model based on Miranda's work that I will describe in a moment, and then using a population model of EEG to try to understand the impact of stimulation on the end result, which is EEG. So actually, we started from some models of EEG that were already available, and this work was actually used to try to reproduce some of the tACS alpha wave stimulation resonances that were seen, and they sort of kind of duplicated those results. But I just wanted to highlight the fact that that we should go in this direction as well, trying to go from the stimulation to the actual physiological parameters that we want in entire brains, if possible. About after effects, since we have the pleasure of having Michael here, I will not say much, just saying that there are long-term effects as well that are plastic, that have to do with heavy and learning. And it's kind of natural that if you alter the firing rates of systems of neurons, you will have plastic effects. There are lots of interesting details on this. So, very briefly, orientation matters. What matters is the electric field that you generate. It's not the currents, really, although they are linearly related, depending on the conductivity. The electric fields move charges around. These accumulate at bottlenecks and create boundary. They create these secondary electric fields, and this happens at cell membranes, for instance. If you want to control the electric field, you need to control the currents. So when you develop a technology to do this, you want to make sure that you have current control systems, which is what we have in the tDCS world now. Most of my talk will be based in this very simple model, which relates linearly the strength of the electric field and the impact on the transmembrane potentials with taking into account the orientation as well. But of course, this is a first-order model, and we need to develop better things. This is hard to do. So for the moment, that's what I use. But I hope that someday we will be able to understand exactly how these other types of neurons with complex geometries and not so obvious directional effects come to play. Okay, but following this first-order model, tCS, I'm going to take it as being mostly cortical in nature, and I will focus also on the normal component of the electric field to the cortical surface as the primary driver of effects, okay, which is aligned with the cortical pyramidal neurons, which we will presume are the main actors. Okay, I will skip this, I think. In terms of modeling, tACS and tRNS can be modeled in a way very, very close to tDCS because we are under this quasi-static approximation, which means that the dynamics of the currents are not going to play a big role in terms of more complex physical phenomena. So the same models that we'll be talking about apply to both DC, AC, and tRNS. Okay, so in terms of models, we have just a little bit of history. So we have this pre-finite element modeling, which is now what is being used mostly. We have these spherical brain models, which started, I think, in 1969 is the first one that I could identify. And there's a series of other papers that try to model, and they did model quite successfully these electric fields by using these concentric sphere models. FEM modeling arrived, as far as I can tell, in 2006 with this first model by Tim Wagner. And then in 2000, this was a realistic or semi-realistic head model. This was a spherical model, but also using FEM. And then in 2008, this was used to to start modeling these more focal arrays and so on. Okay, then I think in 2010, this was the first time that I think a realistic head model was used to actually compute electric fields in the brain. And thereafter, there have been many papers and a lot of work, and it's all very convergent. So I think that the technology is mature now in that sense. There are some open questions still, but it's ready for implementation into systems that are out there. And in our company, we have implemented basically this model so that you can in real time visualize, try to infer what you're doing by using different montages. So this part is pretty mature, I think, and gets us ready to go to multi-channel systems, which is what I want to talk about mostly today. So this sort of started in 2008, where we, in a project which was about brain-to-brain communication, and was very interesting. We were very fortunate to have Michael as a reviewer of the project, actually. The goal was there to develop technologies to actually do more controlled stimulation. So we knew we wanted to have something that was multi-site. We wanted a technology that was where it was possible to control independently at each channel frequencies, intensities, phases, and so on. And we also wanted to use small electrodes, EEG-like electrodes, for more focal, more control effects. And we wanted to measure EEG and at the same time be able to model what was happening well. So this is the origin of the technology. So we did it. We developed this system. I just wanted to illustrate here a recent paper, just one that I picked out because I was reading. It was interesting, trying to understand the functional role of alpha oscillations in creativity, and they use this montage in which you have two electrodes here in phase and one in counterphase, and they use some kind of electric system, lab system. But it is now possible to create this montage and put it in motion very simply by using technologies such as the one that we have. You can also add, have stimulation with waveforms which are the sum of different frequencies. So in this case, for instance, I'm illustrating here a stimulation in which you have one electrode here at one frequency and one electrode at another frequency, and here you have the sum of the two. So you can have the superimposed slow and fast oscillations if you want. You can control phases as well, which is one of the things that we also wanted to do. So in this case, we have an eight-channel stimulation configured. I think it just went back. Yeah. Some of them at 0 degrees, 120, 180, and 300 degrees of phase relative to each other. And this is kind of the picture here. I think it's what it looks like. It's kind of fun. I call it the Christmas tree. Let me see. It stops. Oh, well. Doesn't like that. Okay. What it's doing is actually having the intensity of the electric field going from front to back and around. So you have this kind of traveling wave that you can put on the cortex. Okay, targeting discrete targets. So this is the idea of trying to be more focal, and some of the ideas that have come up again in bringing together this EEG-tCS analogy is from the Laplacian electrode. Which is something that was proposed by Hort, I hope I pronounced it right, in 1975 already, and in which they show that by using these 4x1 or ring electrode systems, you could actually focalize try to get more sensitivity to sources which were local under the electrode. Okay, this same idea has reappeared in tCS non-coincidentally. And this was actually in 2009. There were two parallel papers, one from Pedro Miranda and one from Data and Maram's group, in which the same 4x1 montage was proposed to try to get more focal results. Okay. Some word about lingo. So here you have heard the term HD tDCS, and you have heard me use the term MTCS. Well, I think originally the term HD was used in the original papers, as I can read. It was more used to refer to this 4x1 stimulation, this Laplacian electrode type of system. But now I think the term is used, and I think Maram can confirm that is basically used for multi-channel stimulation by using small electrodes. So I think, I apologize for having to use different terms. I think we should converge on one and that's it. But we're basically talking about the same thing. Okay, so optimization. So if you want to hit a single target, how do you optimize that? So there's a series of papers that started by looking, by using Venn modeling. If you have two electrodes, how do I put them? I mean, how do I move them around in order to target the area I want? There were other papers, well, basically doing the same kind of thing, but not by using two electrodes, by many electrodes, try to find the optimal current distribution to hit a target. We proposed our own system some years ago now. Well, we developed it partly in the Hive project, which is kind of a generalization or a slight departure. The main particularities that it has is that it requires you to define a target map that can be discrete or extended, and to attach to it a weight map. So you specify for each region that you want to stimulate how much you want to hit it, how important it is to you, and then search in the space of electrode configurations for the best match. Okay, and the other particularity is that we really focused on the notion of the normal component of the electric field at the cortical surface, which, as I mentioned before, is what I think is important in this area. Okay. So one of the particular, I mean, in terms of implementation, we use some genetic algorithms to look for the best distributions of electrodes if you have a subset of them. And we really adapted the methodology now to our system, which allows for up to 70 electrodes now. Okay. So I want to give you some examples of what this does. So here's a target that is the left dorsolateral prefrontal cortex target, and I want to show you a little bit what you normally done with classical sponges. These are classical sponge setups. Well, they are actually circular sponges, right? They are a little bit different from the rectangular ones, and this is the target right here. And you can see here the electric field that you're generating with this montage. This is a slight variant in which you use the contralateral orbit for the same. And as you can see, that's a little bit better, but it's still pretty bad. And this is an optimized two-electrode solution. So this is a solution in which you let the system find the two electrode positions and the current so that you get the best match to this area. And it does quite a bit better, even though you're only using two small electrodes. The criterion here is that the match, the normal component of the electric field generated should match the target, and it should avoid hitting other areas. So it's an optimized system in that direction. Here's the same with 5 electrodes now, and this is the electrode positions that you get, and this is the electric field that you get, which now starts to look pretty similar to your target. If you add 3 more electrodes, you get a little better. If you add 39 channels, in this case, you don't gain a lot, really. Okay. If you're interested, we just posted a white paper on this, showing different montages for the dorsolateral prefrontal cortex and the motor cortex. Okay, now targeting going for networks now. We heard some talks a minute ago about the idea of targeting networks. And I will give you here an example. I don't know, why is this? Okay. So let me go back forward, because the idea starts here. It's in this paper from Mike Fox and some other colleagues from Pasquale Leone's group, in which they show that the efficacy of transcranial magnetic stimulation, that this was discussed in the talk before, is related to how close you are to areas that correlate highly with a seed in the subgenual cingulate. Okay, so from this kind of thinking came the idea. Okay, let's and what I want to emphasize here is that the areas that correlate with this deep brain stimulation target it's not just one. There are several of them. So the idea was, why don't we use tDCS to act accordingly? So I mean, it's clear that in areas that anti-correlate, you should do the opposite than what you do in areas that correlate with the target. Okay, so we use this T-map as a target, and we find the optimal solution for this target. And well, it's in the paper that this is published in. You can find the details, but here's the resting state functional connectivity map. This is the classical montage that is used to normally try to treat depression with tDCS, and as you can see, it's doing a pretty bad job at actually having anything to do with this target map. And this is, I think, an 8-channel solution, which, as you can see, is starting to hit, well, as you would expect, the areas that you see in red. You have anodes in them, and so on, and you have cathodes and the other ones, and so on. And the correlation, we have this concept of weighted correlation coefficient between the created electric fields and the target map, and the traditional one has a pretty low correlation coefficient, and we can get quite a bit better with these multi-channel systems. Okay, I'm going to skip this. So this was just it's a methods paper, and what I want to emphasize here, this is another paper by Mike Fox, in which he did a presentation of the different resting state functional connectivity maps that have to do with different pathologies. So this gives us a lot of interesting playground to study or to try to optimize montages for this. So this is it's still research to be done. Okay, so that was the part about networks based on fMRI or PET and so on. I want to talk a little bit about EEG now. So as I mentioned before, at least in the model that we have in our heads right now, or at least some of us have in the head, that pyramidal neurons are the main guys that are sensitive to DC, and they are also the community of neurons that is responsible, is believed, of EEG, scalp EEG. And the fact that these guys are aligned and coherent spatially and temporally is what gives rise to these strong EEG fields, scalp potentials that you measured. And it is also what makes them especially sensitive to tCS. So this is very interesting, I think. So you have quite a few reasons to study EEG in tCS research. So you can use it to compare changes in EEG before and after tCS, and during tCS is also possible to do it. You can explore the impact of different frequencies, different phases, and many things. You can use the impact of TMS after or during tCS using EEG techniques. You can use EEG to develop dosing strategies, to develop targeting strategies, closed loop systems. Okay, so there are a lot of interesting things to be done. Here's an interesting paper. That is the one that actually drew me into the field by Marshall et al., in which they showed that boosting slow oscillations during sleep could potentiate memory, but actually in this paper you can also see very interesting effects on EEG, both during stimulation and also in synchronization. Okay, so you have entrainment effects in this paper. In this other paper by Michael, I'm just showing a couple of papers on EEG and tDCS. The connectivity changes due to tDCS were explored, and that's also very interesting. There are studies also with ERPs that both in humans and in animals showing very interesting changes in evoked potentials. And it is now possible to actually measure EEG during tDCS. At least that's our experience with our system. We can here is an example of the EEG from a subject with the stimulation off and the stimulation on, and with eyes closed. And in both cases, the EEG traces are very similar, and the spectrum is also very similar. So we haven't encountered that many problems, but you have to use this special, these argentum chloride electrodes, both for stimulation and for EEG, in order to get good readings. I wanted to mention something. It's more from the physics side, but I think it's interesting, on the reciprocity theorem, which you might have heard about before. And this is a very mind-bending theorem, but which is, I think, is worthwhile thinking about and explaining. So if you have an EEG system with just imagine they have a dipole in the head that is generating some EEG, right? It's generating a scalp potential, which I call here VA. And if you actually stimulate, if you inject a current at the same point, this is going to induce an electric field at that point that we were talking about before. You can write this equation that says that the product of the scalp potential times the current is minus the dot product of the dipole generator and the electric field that is induced. Okay, so this is telling you that you can basically inject currents here and measure voltages there, or do the opposite, and you should get the same answer. Okay, and this is a theorem from 1853, and it has been used quite a bit in the EEG community for things like trying to do the inverse forward modeling from dipoles into scalp potentials and so on. Okay, and we can actually generalize this to the question of what happens if you are stimulating at several places at the same time, and what happens if you have many dipole generators. Can you say something about that? And it turns out that yes, you can. So here's the generalized equation, and I haven't checked, but I haven't seen this written anywhere else. So, but it basically says that the sum of the products, so it's the same equation as before, but you have to sum over the scalp and you have to sum over the volume. And it's a very interesting equation because it says that you can use it for optimization, okay? So if your target is to create electric fields that are closely correlated to the dipoles that are generating EEG, what you should do is align, so to speak, the currents with the voltages. They have to be parallel to each other, okay? So you have if you have some constraints, like you have a maximal current that you can use and so on, what this equation tells you, okay, if you want to increase this correlation or anti-correlation, depends what you want to do, if you want to excite or or inhibit, then you should basically inject currents that look like the voltage distribution. Okay. So this can be very, very interesting because it can allow you for fast optimization of MTCS, keeping in mind of what you're actually optimizing. So that's a limitation. You have to understand what you're optimizing there. So it's not focality and it's not some other things. It's the correlation of fields with the dipoles that are generating the EEG is what you will be optimized in this case. So you could use it for closed-loop applications. And who knows? I mean, this is just for fun, but I don't know if you have seen this movie, Brainstorm. You could presumably do things like some people have done in vitro, which is to read out EEG and use it to play it back in the brain and see. This can be done in pretty sophisticated ways, I think, and it should be tried. And this theoretical tool also gives you an idea on how to study different questions that are interesting theoretically, which is the optimal number of electrodes to use and so on. And I think I had here a scalp map. Oh yeah, so this is a cortical, it's cortical mapping of EEG, so it's kind of an inverse problem. showing where the sources. This is the first independent component, I think, of an alpha band. So, as you can see, if you want to stimulate the alpha frequency of somebody, it's not going to be as simple as some people have been using, because you have different sources and you have different temporal patterns and so on. So anyways, you could do cortical mapping and then optimization, or you could try to use fast techniques like such as this. Some words about entrainment. By entrainment, we mean this interaction between oscillating systems. And there are already very interesting papers and work in with humans showing that if you stimulate people's brains with tACS at the right frequencies, and this will depend on the phenomenon that you're studying, like Marshall did it during sleep with slow waves. Kanaya and others did alpha frequency stimulation, which is very popular these days, to try to entrain different things. Froelich et al., I think, did a very beautiful work in vitro showing that it's possible to entrain the oscillations in ferrets slices, and actually did this kind of endogenous EEG stimulation at the same time. I think it's remarkable that the electric fields that we use for stimulation are very similar in magnitude and frequency to those which are endogenous in the brain. I think this is telling us something, okay? And this has to do with something called ephaptic interaction, which I will not talk much about at the moment, but how am I doing on time? I'm still okay? Close? 10 minutes, okay. So this is the paper by Froelich and McCormick in 2010, which showed that if you apply external electric fields similar in magnitude to those endogenous ones, or even if you inject the endogenous ones, you can entrain the oscillations of these in vitro populations. In humans, there have been some papers with alpha stimulation. Here's an example from Zaele, which was one of the first ones. This is the montage, using large electrodes again, and in the occipital region. And they use a paradigm in which the pre and post EEG measurements were with eyes closed, but for the stimulation they kept eyes open, and they saw an effect in there. More recently, there have been other more sophisticated papers now that are using different paradigms with eyes open mostly, and that also see this effect of amplification of the alpha frequency by using the personal alpha frequency. In this case, the montage is very different, as you can see. So it's a front-to-back montage. This is another one which I find very interesting. And we're actually doing similar work now, in which it's a montage like in Zaele. I think it was all eyes open. And they actually use this interleaf stimulation paradigm. So they stimulated tACS, measured EEG, and repeated this many times, trying to answer the question if there is a resonance effect. So if you have a resonance in nature, like in a bell, if you hit it, or if you stimulate it with the right frequency, it will resonate, and this resonance will continue to will outlast the stimulation. It will be there for a while. And they were trying to see if the effects of tACS was kind of this kind of dynamical resonance, or if it had more to do with plastic changes. In their work, they concluded that it was plasticity, because they couldn't see any entrainment right after the stimulation. I don't think the case is closed yet, because actually measuring EEG in this regime here is very difficult. So it's a technical challenge. Okay, this was the point that if you want to stimulate with tACS in any of these experimental protocols, you have to keep in mind that the distribution of sources is going to move around the cortex. It's going to have its own spatiotemporal idiosyncrasies, and you need to take into account in order to to stimulate correctly. So it's not as simple as putting 2 electrodes on the occipital region and hope that that's going to do it. Okay, so this is my last slide, actually. Just to wrap up. So I try to convey the idea that models represent the state of the art now in our understanding of tCS. They are not perfect, and I would call them like a first-generation model. I'm talking about the biophysical model of how the electric field interacts with neurons, and also the propagation of currents, which have some shortcomings still. They will be improved over time, but they are much better than nothing, and I think we should be using them and not, as opposed to not to. Targeted multi-electrode montages using small electrodes offer the opportunity for more precise, targeted, controlled, reproducible stimulation. So I think we should be using them and not, again, large pads with very uncertain positions and very scattered effects. Brain function is mediated by networks. This is a theme now that's out in the open, so we should try to go after them, and I proposed some ideas on how to use target maps from resting state functional connectivity MRI, from PET, from EEG, and so on. And we have the technology now to, once we have a target map, we have technology now to optimize the stimulation protocols for that. The combination of EEG and tCS is quite natural and powerful, I think, and there's a lot of work to be done. The same approaches can be used not only for tDCS, but also for tACS and for tRNS. And there are many, many questions still that are open for exploration. So, mahalo. Thank you.